Okay, this is 4.6, optimization. So this is very similar to related rates. We're going to apply what we learned to real life situation. Optimization means we are going to find the best way to do something. How can we maximize the profit? How can we minimize the cost? How can we maximize the area? Something like that. We're going to optimize, make it the best possible. Okay, and because it's a real life situation, you're going to have to think real life. So, like for example, what's the highest width that can maximize the area? You're going to not choose negative numbers because that's not real life, or choose 0 because that just means you have nothing, right? So kind of think in real life situation. Okay, so kind of like some related rates problem. They're all word problems, so I give you a sheet of all the word problems so you don't have to copy it. And this last time I saw you guys write all the answers on that sheet of paper with very little space. So I gave you some space on the questions now. You can just write on there if you want. Okay, first one. So all these questions obviously has to do with what we learned in this chapter, which is all about critical points, maximize, minimize, concavity, all that stuff. We're just going to see how we are going to apply. Okay, so the first question. A farmer has 2,400 feet of fencing and wants to fence off a rectangular area field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Okay, so draw a picture first. He has this river. He wants to build a fence along the river. He doesn't need any fence on that side that has the river because he says the river is good enough. So he wants to figure out what's the dimension of this fence or this rectangular area so that he can use up all 2,400 amount of fence, but he will get the largest area. So basically, you can draw this fence any way you want, right? And create 2,400. But only one of them is going to give you the largest possible area. Okay, so the question is, how do we do that? All right, we have two things. We have two things. We have area and we have perimeter. So first, let's just kind of label these things. I'm going to label this X and then 2 Y's. You can label them anything you want. Okay, the perimeter is what? It is 2,400 and according to X and Y? 2Y plus X. Okay, and then in this plot, what is the area? Formula. XY. All right, now when you look at the question, this is the key. Largest area. They want the largest area. When they say they want the largest area or the smallest area or something like that, they're looking for maximum. All right, so think about the the whole last week and the week before break. We've been doing maximum, minimum, right? Maximum and minimum has to do with what?
Change of sign for the derivative graph.
Yes, so we are looking for first derivative. Okay, whenever they say maximum, minimum, we're looking for first derivative. And what kind of points are we looking for? Silence. Maximum point and maximum point or minimum points only occur at where? Critical point. Okay, so we are going to take the first derivative. We're going to find the critical point. We're going to create a sign chart and see if that's a maximum. Yes? Okay. Well, we're taking a derivative of which one? There's a P and there's a A. What does the question say? Largest what? Area. So we're taking the derivative of P or A? A. Well, if you take the derivative of A, there's X and Y. Well, it's going to be hard to do if there's X and Y. So what can we do to eliminate one of the variable?
Using the P substitution.
Substitution. So we can use P and then substitute into A, so then we can just have one variable in A. So these kind of questions always have two equations, and they seem to be not related. They will only want to maximize one of them. So you're going to use the other one to substitute. That way you only have one variable. Okay, so really doesn't matter which one we substitute. I'm just going to do the easy one. So x is equal to 2400 minus 2y. And then I'm going to substitute. So that is 2400 minus 2y times y. Again, make sure you look at the question. They will always tell you which one do I want to be the largest or which one I want to be the smallest. It will only be one of the equation. The other one is just used to substitute. All right, so this is 2400y minus 2y squared. All right, what do I do next?
Find the maximum.
Find the maximum by doing what? Derivative, good. So I want the derivative. There is only one variable, so my variable is just y. So 2400 minus 4y. All right, now that I have the derivative, what am I supposed to do next?
Critical point.
Critical point. How do you find critical point?
Once
Say equal to 0. Say equal to 0. Okay, so this is 2400 equals 4y. So y is equal to 600. All right, let's just double check to see if it is the maximum. So we're going to create a sign chart. All right, so number smaller than 600, so let's use 0. So if you put in 0, what's the sign? Positive. Am I doing this right? Okay. All right. And then if you put in a number that's bigger than, let's say put in 1,000. Negative. All right. So this is going to go increasing and decreasing. So is 600 the maximum?
Yes.
Yes. All right. So let's go back to the question and see what they want. Oh, yeah. Question.
So how do you know it's not like 500? Is it because it's not like a critical point?
Great question. All right. So the reason we're using critical point is because by definition, critical point is always the maximum or minimum. It's basically the part that's going to give the derivative a 0, right? So there is no other number that is going to be as high or as low as the critical point. Yes, that's why we use the critical point. Okay, so the question says, what are the dimensions of the field? So they want the length and the width, or in our case, x and y. So we know that y is 600. How do I find x? Plug it back in. So I have here x is equal to 2400 minus 2y. So 2400 minus 2 times 600, that is 1200. So that's my dimension. Yeah.
You need to write the unit.
That would be nice. But basically, if they don't say unit on the test, then you don't have to worry about it.
Then wait. You said 12.
So the question is, what are the dimensions that will give you the maximum?
Plugging back to the P.
P, yeah, you can, but P is 2400 equals 2y plus x. Y is 600. Good? Okay. So your homework tonight is all this kind of problem. So this is the easiest kind of problem. So we're going to practice that a lot for a day. We're going to spend 3 days on it because it gets very hard later on. But these kind of questions are pretty easy. So we'll just work with that for a few days. Yeah.
We have to use the derivative.
We do. Unless you graph it. You can remember, you can always look at a graph and say which part is the maximum, which part is the minimum. That
So
also
I need
works.
to graph it, or I need to like the maximum.
Yeah, but these kind of questions, if it's this simple, it's on the test is usually no calculator. Okay, next one. This one gets a little bit harder. A cylindrical can is manufactured to hold 1 liter of oil. Find the dimension of the can that will minimize the cost of the metal to manufacture the can. Okay. Huh?
It's a volume, right?
Yeah, so there are a few things, right? So first, we want to draw the can. Just kind of look at what we're dealing with. Okay, now look at, so like I said, they will always give you information on 2 things that would give you 2 equations. Okay, so if you look at the question, it says this can is manufactured to hold 1 liter of oil. 1 liter of oil means what? Is that area, volume, surface area, what is it? Volume. So volume is 1 liter. Find the dimension of the can that will minimize the cost of the metal to manufacture the can. So they want to minimize what?
Surface area?
Surface area. They want to minimize the cost to make this can. So think about what holds the can. It's the outside and the top and bottom, so that is the surface area of the can. Okay, so let's just use A. Okay, what is the volume formula for a can, a cylindrical can?
Pi r square h.
Pi r square h. Okay, the area times the height. What is the surface area? Surface area is a little bit harder because you have to think, oh, I have this can, the surface area on the outside, and I have the lid top and bottom.
2 pi r squared plus pi r l.
2 pi r squared, so that is each of those pi r squared, there are 2 of them.
Pi r l.
Well, let's use h. Not pi rl.
2 pi r.
2 pi.
2 pi r, that's the circumference, times height. Plus, yeah. So plus the circumference, 2 pi r, times the height. Are you guys good? Surface area? Okay, so 1 liter. Okay, 1 liter is 1,000 centimeter cubed. Okay, so now let's go back to the question. They want to minimize what?
Area.
Surface area. They want to minimize the surface area. So what are we going to do with this A to minimize?
Like define your minimum.
Find the minimum by,
Converting to critical point.
okay, critical point. Yeah, eventually, yes. But we are going to take the derivative. Well, if you take the derivative right now, we have 2 variables, right? We have R and we have H. So what are we going to do? Substitution, right? So we're going to use the first equation and do some substitution. Which one into which one?
H equals 2.
Yeah, so you want to solve it for H because H is a little easier. You can solve for R too, but you're going to get a lot of square roots that you have to take derivative of. It's just a little harder. So 1,000 over pi r squared. Okay, now let's plug it in. 2 pi r squared plus 2 pi r times 1,000 pi r squared. Okay, before we do anything, let's just make sure we simplify so it's easier to do. 2 pi r squared plus 2,000 over r. Okay, again, we are looking for the minimum surface area. When they say minimum, they meant take the derivative. Okay, so go ahead and take the derivative of A.
Oh, why do I need to put 1 liter into 1,000 centimeter cube?
Because we're trying to find the dimension of the can. 1 liter is not in any kind of dimension, like length. Yeah.
But Can I just like use 1 liter to solve the question first
And then substitute in?
Yeah.
Yeah. What is the derivative?
4 pi r minus 2000 over r squared.
Wait,
Is it
2 pi r minus 2000 over r squared. Because you can change this to 2 pi r squared plus 2000 r to the negative 1. So when you take the derivative, remember to subtract 1. All right, let's find the critical points. I'm going to combine them together as one big fraction. Oops. Okay, critical points is what makes the numerator 0, what makes the denominator 0. Okay, so go ahead and find your critical points. Okay, so where are my critical points? R equals what? Can you guys give me the number without decimals?
0 and 11.6.
Without decimals.
11.12.
No. I mean like the exact answer. Don't use the calculator. Cube root, not 50. 500. 500 over pi. Okay, those two numbers. Obviously, 0 cannot be the answer, right? It is a critical point, but obviously 0 cannot be the answer because if you have nothing, of course you're going to minimize, just don't make the can, right? But it just is not a very, I guess, interesting answer, or it doesn't make any sense to just say like, how do you minimize the amount of cost to make this can? Don't make the can. That makes no sense. So just put them on there to draw your sign chart, but don't use 0, okay? And then obviously there's nothing less than 0. You cannot make negative amount of cans. Okay, so go ahead and draw your sign chart and figure out which R is going to minimize the cost of the can. All right, so there is nothing that is less than 0 because we do want to make the can. And it goes minus plus, so R equals cube root 500 over pi is going to minimize the manufacturing of the can. But we do need to also find H. Okay, H is 1000 over pi r squared. So go ahead and find out what H is.
What if you just use the calculator?
Oh, yeah. Go ahead and just use the calculator. Okay, R is 5.419. H is 10.839 about, which is actually just 2R. So that's going to minimize the surface area of the can. If you plug it back in, you'll see that it's 2R. All right, let's try another one. The next one is very tricky. Find the point on the parabola y squared equals 2x. That is closest to the point 1, 4. All right, let's look at what this looks like. I'm going to do this on decimals. Okay, yeah. Okay, so we know that this graph kind of looks like this. We have this point here. The question is, which point on this parabola is going to give me the closest distance? Okay, this point is 1, 4. Somewhere on this parabola, we call that just xy. So we want the closest distance. Can you think of a way to figure out a distance between 2 points?
They have the same slope.
Not same slope. How do you find the distance between 2 points?
y2 minus 1, 1. Plus x2 minus x.
Ooh, so close. y2 minus y1 and then Huh? Yeah, squared. Okay.
Oh, square plus x2 minus x1, and then the whole thing.
Oh, square first again.
The
And then
square, then the whole thing is to the
1/2.
1/2.
Yeah. So this is the distance formula. So to find the distance between 2 points, we use the distance formula. So the question is, how do I find the point that is closest to this point? Closest to this point, what are they talking about? They want maximum or minimum? Maximum distance or minimum distance?
Minimum.
Minimum. Okay, they want the minimum distance between these two. That means we're going to have to take the derivative of d and then find the minimum. Well, like I said, you always have two equations, and then you're going to have to do some substitution, right? So I only have one equation here. Where's my second equation? Huh? Y squared equals 2x. Yeah, so in the original parabola. Y squared equals 2x. So we're going to have to do some substitution into the distance formula. That way we can take the derivative and solve it. You're not looking forward to this, huh? Okay, well, we got to solve that. Y squared equals 2x. What should I do to substitute?
X equals y.
Yeah, x equals y squared over 2. All right, so distance formula now becomes, oh, I got to put some numbers in my distance formula, right? I have all of these y1, y2s. I'm going to make the 2's the actual point. So 4 minus y plus 1 minus x. And that's all squared. Okay, x is equal to y squared over 2. So that is 4 minus y squared plus 1 minus y squared over 2 squared. Okay, I need to take the derivative of this one. That looks horrible. So here's what the textbook says as a trick. They said just square everything. Just square everything. And then now when you take the derivative, you're just trying to find the minimum of the d squared, which is still going to give you the same number. It's just a trick to make the algebra easier, or the calculus part easier. Okay, so we're going to square it so it's easier for me to take derivative.
So when we take the derivative, is it 2p?
No, we want to find the minimum of the square. So just like that, that's it. All right, we'll finish this problem tomorrow.